we actually derived our energy equation, right? And now what we're gonna do is, as I promised here, after we wrote down or derive our energy equation, we said we are gonna apply it to the thermal boundary layer. Okay, we're gonna do similar things that we have done for the momentum boundary layer. Okay, so let's call it page 3. And let's say application of the thermal energy equation to the thermal boundary layer or a flat plate. So that's what we're gonna do. Let's draw the schematics for the hydrodynamic boundary layer first. V infinity, T infinity. We said that this is the thickness delta X, right, at X. We said that you can draw the velocity profiles using arrows, and the length of the arrow corresponds to the size of the arrow corresponds to the velocity, and you can do it for like at different positions. Okay, and this layer is called hydrodynamic boundary layer edge. Okay, and this is your plate. And imagine that now we are going to actually have a look at the temperature profiles. And so we have let's keep the plate at the temperature of T-wall, and assume that the T-wall is much larger than the T infinity, so the wall temperature is larger than the fluid temperature. Okay, now let's do the same thing for the temperature profile. So you have a plate here. The plate wall is kept at a temperature T-wall. Okay, and you have some sort of profile here, like a boundary layer. This is, let's call this thermal boundary layer. And let's call this thing as the thermal boundary layer edge. Okay. And because I'm going to use the spot there. So T-wall is much larger than the T infinity, so this is our T infinity. And again, this is our y direction, and let's call this thing as the delta T, analogous to the delta for the hydrodynamic boundary layer. And this time the temperature at the wall is larger. So you have, although this is not a vector, let me use like let me denote the amount of temperature as the size of these arrows, and when the profile becomes actually flat, it means it's the end of the boundary layer. Okay, and if you evolve, then what's going to happen is basically the heat transfer is going to diffuse deeper and deeper into the fluid, right? That's why you have a larger boundary layer thickness at a larger x. So this is my T wall. So this is my T wall. Okay. And this goes on like this, where the profile becomes flat. So the profile becoming flat means the following. There is no sense of any like heat transfer around this, meaning that the plate is not felt by the fluid at this point, right? Similarly, here, the plate is not felt at a larger distance now, because most of the heat is being transferred to the like this part. So like as you evolve as you go in this direction, then the effect of plate is being felt at a larger and larger distance. Okay, so that's the essence of the change of the boundary layer thickness with the x. Okay. And these arrows are just for convention. Temperature is a scalar. So I should have not actually shown like arrows for that. Not a vector. Okay, unlike the velocity. So well, I might actually show it without the arrows. So, but just take it with a grain of salt. Okay. Or you can say, okay, let me erase this. I don't want to do it again, but you can erase the arrows and like make them lines. Okay, similarly for this. And let's say no arrows. Okay, good. We corrected that. Now, you can say like, so this is the delta, the boundary layer thickness for the hydrodynamic boundary layer. This is the delta T. And you can say, how is the delta T related to delta X? Right, that's one question we should ask. How is delta Tx related to delta X, right? This is thermal boundary layer thickness. And this is hydrodynamic or momentum. Boundary layer thickness. Okay. So now what did we get so far? Now the equation that we get was for the delta X. Remember, we had what was the equation? Let me remember. Okay, let's first simplify this equation that we got here in the previous one. This equation I'm going to rewrite. Okay. We x del t over del x plus Vy del t over del y is equal to alpha del squared t over del x squared plus alpha del squared t over del y squared. Okay. Now, if you remember, for boundary layer theory applied to the hydrodynamic boundary layer, hydrodynamic conditions, we assume delta is much smaller than L. We're going to do the same thing. So for the thermal boundary layer, for boundary layer theory applied to the hydrodynamic boundary layer, we assumed delta is much smaller than L. Now, for analyzing the thermal boundary layer, we will assume delta T is much less than L. Okay. Now, what happens to these equations in this with these assumptions? Now, let's have a look at this each and every term one by one, like the this term, this term, this term, and this term, and let's see how they change. How they can be approximated. So del squared t over del x squared term, the first term on the right hand side, you can approximate it as t vol minus t infinity divided by L squared. This is like order of magnitude estimation, right? It's just a rough, very crude estimation. So the del squared t over del x squared scales with the tw minus t infinity divided by L squared. And that's, we can call it like delta t over L squared. Like tw minus t infinity, from now on, let's call it delta t for the sake of simplicity. The second term, part of the second term on the right hand side, del squared t over del y squared, will be approximately delta t over delta t squared, right? Roughly. It's gonna scale with that. So we are basically doing a crude scaling analysis. Okay. Now, if you compare these two terms, this and this, in other words, this and this, you will see that this term is different, right? And since delta t is much less than L, then delta t over delta t squared is going to be much greater than delta t over L squared, right? This implies that we can ignore this this term, right? Ignore delta t over L squared compared to delta t over delta t squared. So this survives, but this can be neglected. In other words, this survives, this can be neglected. Okay, in other words, this survives, this can be neglected. So let's rewrite it. Thus, with the assumption of delta T much less than L, our boundary layer equation, energy equation, becomes Vx del T over del X plus Vy del T over del Y is equal to alpha del squared T over del Y squared. I got rid of one term, so it's simpler now, right? From our previous analysis for the momentum transport, delta was determined by nu, the kinematic viscosity, right? But instead, in this equation, we have alpha instead of nu, right? Analogously, now the delta T should be determined by alpha, the thermal diffusivity. Right? This is also another type of diffusivity. This is the momentum diffusivity, right? So nu is momentum diffusivity, alpha is thermal diffusivity. They are analogous to one another. And what did we say about the relation between the two? I mean, for example, when the nu is higher, what happens to delta, for example? The higher the kinematic viscosity, meaning that lower the Reynolds number, right? The greater the distance, right? The greater the boundary layer thickness is, or in other words, the greater the distance in the y direction, up to which the effect on the flow by the plate is felt, right? That's basically like how large is your boundary layer thickness. Analogously, the higher the thermal diffusivity, the greater the distance up to which the effect of wall temperature is felt. Right? Now I want you to actually think about the similarity between the two equations, right? So this equation we derived for the thermal boundary layer, but for the momentum, what was the equation that we had derived? Let's see. We had this equation, right? Have a look at this. It looks very, very similar to our new equation, right? Let's write it as well. In comparison, like let's say, compare this with the equation for momentum transport. What was that? It was Vx del Vx over del x plus Vy del Vx over del y was equal to nu del squared Vx over del y squared. So have a look at the two equations. It's very similar, right? Instead of t, you have the Vx in the other equation, and alpha. Instead of alpha, you have nu. It's exactly the same equation, almost. Although in one equation, you have the Vx coupled with t. In the other equation, Vx is not coupled with t. But if you think that, for example, Vx has the same profile as the t, then it might be possible that they have the same solution, right? But let's just go with the analogy for the time being. And this way, like have a look at this alpha analogous to nu, right? And we say that the delta t and like whatever delta t is to nu, whatever delta is to nu, delta t is to alpha, right? So we expect delta over delta t to be related in some way, not necessarily proportional to, related to nu over alpha. And that's a dimensionless number, and we call it nu over alpha. We have actually described this, defined this before. It's Prandtl number. Which is denoted as PR. So Prandtl number determines whether delta is larger than delta t, delta is equal to delta t, or delta is less than delta t. May determine. Now, let's write down all the equations then, right? Hydrodynamic and thermal boundary layer equations. First of all, the continuity equation, del Vx over del x plus del Vy over del y is equal to 0. And then the x momentum equation, Vx del Vx over del x plus Vy del Vy over del y is equal to, oops, sorry, this is Vx del y is equal to nu del squared Vx over del y squared. And the thermal boundary layer equation is Vx del T over del x plus Vy del T over del y is equal to alpha del squared T over del y squared, right? Now, you can actually say that this is like linear differential equation, right? Linear differential equation. Because if you know the Vx and Vy, which is not definitely like T's, right? You're basically having prefactors which is not a function of temperature. It's just a function of x. If you know that, it can be taken as linear differential equation. But this one, on the other hand, you're having the derivatives of Vx and multiplying with the function Vx itself. So this is nonlinear differential equation. That's one of the differences between the two. Second order nonlinear differential equation. And also here, T is coupled to Vx. But here, V is not coupled to, like Vx is not coupled to temperature. Okay. So those are the two differences between the two equations. How about the boundary conditions? Maybe, I mean, although these equations look quite similar, maybe the boundary conditions are different. Let's see. At y is equal to 0, oops, we know that Vx is equal to 0, right? That's the no-slip boundary condition. And similarly, for the temperature, T is equal to T vol. So in one case, the velocity is fixed. In the other case, the temperature is fixed. So that's the similarity between the two. At y is equal to delta, Vx is equal to V infinity, right? Okay. Okay, now, but what about the temperature? We say that at y is equal to delta, like delta T, the temperature is equal to T infinity. Okay, again, like a fixed value for T and fixed value for V. Okay. So let's summarize. Now, we can clearly see that the x momentum and temperature equations are analogous, right? In fact, if nu were equal to alpha, imagine that nu and alpha were equal to each other. Like if one is 2, the other is 2. Like imagine that they are the same numbers, right? Then what happens is can see that Vx and t may even be the same function. If the boundary conditions were equivalent. Let's say are equivalent. But they look like they're not exactly the same, right? They're like V infinity is not necessarily equal to T infinity. Like more importantly, they have different units, right? But maybe changing variables and maybe making them non-dimensional might help, right? So the idea is, let us now transform our variables, I mean Vx and t, such that boundary conditions become equivalent. So instead of having, for example, 300 degrees centigrade, or maybe, no, 300 Kelvin, and for the velocity, sorry, for the temperature, and for the velocity, for example, 1 meters per second. So they are not comparable. Instead, let's actually use like reduced or non-dimensional velocities to make them actually comparable. Okay. So we are gonna scale it from like 0 to 1. Let's scale this from 0 to 1 as well, so that they actually come to the same scale and they're gonna be comparable to each other. So let's see how we can do it. That's the actual beauty of the non-dimensionalization and the non-dimensional numbers. Let Vx tilde is the non-dimensional velocity, is equal to Vx over V infinity, and theta is equal to T minus T wall divided by T infinity minus T wall. I could have chosen this as well, like theta is equal to, there are different ways to do it. I can also do like T over T infinity. That's also non-dimensional. I can also do T minus T infinity divided by T wall minus T infinity. So like the other way around, so the other version of this. Do you know why I'm choosing this instead of these ones? Any idea? Like I'm designing this in such a way that when T becomes equal to T infinity, I get 1 for this. I want to get theta is equal to 1 here, and I want to get theta is equal to 0 here. The reason is because I have the Vx 0 and the Vx tilde gonna be 1, so I want to make them like the same. My aim is to make the non-dimensional temperature the same as the non-dimensional velocity. Okay. Okay. So that's why I choose this one and I don't choose the others. Okay. So our boundary conditions become at y is equal to 0, my Vx tilde becomes equal to 0 again, and my theta becomes equal to T wall minus T wall divided by something which is 0. Excellent, I have the same boundary condition. And similarly, at y is equal to delta, Vx tilde becomes equal to V infinity divided by V infinity, which is 1. And if I assume that delta t is the same as delta, then my boundary condition for the theta is going to be at y is equal to delta t, or delta theta is going to be equal to t infinity minus t wall divided by t infinity minus t wall, which is 1. Excellent so far, right? And also let's define there's one more variable that we didn't take care of, which is the Vy. Define Vy, non-dimensional Vy is equal to Vy divided by V infinity again. So we are dividing by the same number. So substituting these into the x momentum equation, by the way, can you hear me? I'm asking because from time to time my screen shows like waiting signal, or maybe like poor connection. I don't know. Can you hear me?
Yes, we can hear you.
Okay, great. Okay. So what happens is, let's go to the equation Vx. So let's say Vx del Vx over del x plus Vy del Vx over del y is equal to nu del square Vx over del y squared. But instead of Vx, let's write down V infinity times Vx tilde. I use this one again for this too. For the Vy, let's use V infinity times Vy tilde. Okay. Oops. It's x. Okay, there you go. And if you divide all sides by V infinity squared, right, what you get is gonna be Vx tilde del Vx tilde over del x plus Vy tilde del Vx tilde over del y is equal to nu over, there's one extra V infinity, because I'm dividing by V infinity square, not only one V infinity, del squared Vx tilde over del y squared. Excellent. And the temperature equation becomes it was let's see, Vx del t over del x, V infinity Vx tilde del t over del x. Instead of del t over del x, you can use this one to write down del theta over del x times t infinity minus t wall plus Vy, which is V infinity Vy tilde del theta over del x t infinity minus t wall is equal to alpha del square over del y squared theta t infinity minus t wall. And miraculously, we cancel the T infinity minus T walls. Correct? And divide by V infinities. And we get Vx tilde del theta over del x plus Vy tilde del theta over del x. This is del y, I'm sorry. Is equal to alpha over V infinity del squared theta over del y squared. So look at these two equations. They beautifully match, right? Compare the two. This one and this one. Compare. Now, we know that our boundary conditions are exactly the same. And we know that if I take theta as the Vx tilde, and I exactly get the same equation. So if I replace the theta by the Vx tildes, they should also be a solution of the second equation if nu is equal to alpha. Correct? So we say that same governing differential equations and boundary conditions for Vx tilde and theta as long as nu is approximately equal to alpha. And then we say that Vx tilde is equal to theta and then it also means that Vx over V infinity is equal to T minus T wall divided by T infinity minus T wall. Okay, so this is only when nu is approximately equal to alpha. So this is the case when Prandtl number is approximately 1. Okay, and it's very important to realize that nu is a property of the fluid itself and alpha is a property of the fluid itself. And it doesn't have anything to do with like how fast the fluid is moving. It's just exactly which fluid it is. Is it water or is it mercury which is flowing around the plate, which is going to make us argue whether the Prandtl number is 1 or not. So just based on the fluid itself, the type of the fluid, you can argue that you can come up with a fluid which you can actually get exactly the same temperature profile as the velocity profile. Okay, this is something very important and something really surprising, I guess. Right? Okay. And also there is another, like, there is one more similarity. There is one more similarity between the two. If you think about the following, like 1 over V infinity del Vx over del y, if you differentiate, we get del over del y with respect to y at y is equal to 0, which is going to be a quantity that you know, which is the wall shear stress divided by the viscosity, right? the absolute value. It's equal to the right-hand side, if you take the derivative, 1 over T infinity minus T wall, del T over del Y at Y is equal to 0, right? And this is something we already know from Fourier's law. It's the flux, the heat flux at the wall, divided by the K, or it's the absolute value, divided by the K. So you know that this is conductivity is the fluid conductivity. Okay, it's not the conductivity of the solid that's in contact with that, because we're talking about how the temperature profile looks for the fluid side, right? Okay, so basically, the wall shear stress is similar to the heat flux at the wall, right? Let's write them down, where tau wall is the wall shear stress, and Q wall is the wall heat flux. So this equation reduces to 1 over mu B infinity. So you have mu in the denominator, B infinity in the denominator on the left-hand side, times the tau wall. Let's think about the absolute values for a moment, is equal to Q wall divided by K times T wall minus T infinity. This and this are in the denominator. Okay. And we can relate the tau wall to the what was the formula? Let's see. I guess we did this yesterday, and you related the skin friction coefficient to the tau. So you can write instead of tau wall, you can write down 1/2 rho V infinity squared CF, the skin friction coefficient. So 1 over mu V infinity, 1/2 rho V infinity squared CF is equal to, and Q wall is, let's remember, tau wall is equal to 1/2 rho V infinity squared CF, and Q wall is, from Newton's law of cooling, H times T wall minus T infinity, the absolute value of it. So the right-hand side is going to give you H T wall minus T infinity divided by K T wall minus T infinity. I want to actually get an expression for H, because that's one of the reasons that we are actually talking about all these boundary layer theories so far. I want to get this H. I want to have an understanding of what the heat transfer coefficient look like. I want to get some equations that tells me what is the heat transfer coefficient, instead of just assuming some numbers for H. Okay, and now we are getting one step closer to finding H, right? And after some simplifications, you get the following. Let's take CF over 2 on the left hand side is equal to mu over rho is yeah, let's write it down. H over K mu over rho V infinity. Okay, and this is equal to H times, let's multiply it by L and divide by L because I want to make it look like the Reynolds number. And as you can see, this is 1 over Reynolds number L. So this is equal to HL over K. And I want to actually name it. And we call it Nusselt number. It's another dimensionless number, Nusselt number, HL over K. This is a dimensionless number, and it looks like one of the other numbers that we have seen so far, right? Looks similar to bio number, but beware, K is the fluid conductivity, fluid thermal conductivity. Remember, bio number was defined as H L over characteristic over K solid. But this time, Nusselt number is defined as HL over K fluid. Okay, that's very important. That's one of the common mistakes that students do. So if we define this, and it's basically tells us the following. It gives us an idea about enhancement in heat transfer. Over conduction alone. What does it mean? It means what is going to be the enhancement on my heat transfer just by flowing, just by pushing the fluid over the plate instead of just leaving the fluid there without fluid not being in motion, right? So it gives you an idea about what H is depending on what K is. Okay, so if you have a low K but a large H, that means it's just because the fluid is moving very fast. That's why it's helping, enhancing the heat transfer. If that's small, that means all the heat transfer is being done by this fluid staying there like a solid one without any motion. Okay, so Nusselt number. If you know the Nusselt number, you can calculate the H by knowing the K. So if you know the fluid, which fluid it is, you know the K, right? For example, the air has a particular K value. So if you know the Nusselt number corresponding to the flow of the air over some plate, then you can calculate H from the Nusselt number and also the K. Okay. Long story short, this part you can write down Nusselt number L and Reynolds number L to the power -1. Okay. So we have found that Cf over 2 is equal to Nusselt number L over Reynolds number L. Remarkable. What does it tell you? It tells you that, so let's write it down. For Prandtl number is equal to 1, or nu is equal to 1. Sorry, nu is equal to alpha. Okay. Or you can say, okay, if the Prandtl number is 1, let's say, let me write it, incorporate it in my equation. Or you can write Nusselt number L divided by Reynolds number, Prandtl number. Since it's 1, I can just put it in the denominator if I like, because it's 1. So now this equation is remarkable in the sense that if you know the values for the flow conditions, like the friction coefficient, skin friction coefficient, Reynolds number, and if you know the fluid property like Prandtl number, it tells you that you can estimate the Nusselt number, and which you can work back and find out the heat transfer coefficient, right? Let's work a little more about this Nusselt number divided by Reynolds number, Prandtl number, and let's see what it actually means. Now let's write it down. HL over K. 1 over Reynolds number is mu over rho V infinity L. And the 1 over Prandtl is alpha over mu. Alpha over mu, actually. But alpha over mu is nothing but alpha rho over mu. Yeah. So I'm going to wrap up in a second. The time is up. So after simplifications, what you get? The rho's cancel, mu's cancel, rho's cancel, L's cancel, and you get H alpha over K V infinity, right? Okay. And instead of alpha over K, you can write down the alpha is K over rho Cp, right? And then you find out H over rho Cp V infinity. And then let's multiply by delta T both sides, H delta T. I just want to make the numerator look like the Newton's law of cooling. Divide by rho Cp V infinity delta T. And let's have a look at the numerator and the denominator. Numerator is our convective heat flux, and our denominator is the advective heat flux. right? Because this is, this is the amount of heat transfer just by the fluid moving from one place to another. And it has a special name. It's called Stanton number. So in short, the Stanton number, which is defined as, Stanton number equals Cf/2. And this is called Reynolds analogy. Okay. So what does it tell us? Very quickly, I'm wrapping up. If you know what the skin friction coefficient is, or in other words, the hydrodynamic property, then you can calculate what the heat transfer coefficient is. Right. Okay. But the major assumption is in Reynolds analogy is that the Prandtl number is almost 1, or nu is almost alpha.